And finally, the central limit theorem now. Central limit theorem. Everybody knows the statement, let x1, x2 and so on be IID, and I'm going to denote their finite. So first let me put here a finite second moment. So I'm going to denote by m their finite means, and by sigma square their finite variances. They are all the same for each I. Okay, and then the statement is that if I look at the sum of the first n, which is again denoted by Sn as usual, minus the mean of Sn, which is n times m, over the standard deviation of Sn, which is square root n times sigma, then this converges, the law of this converges weakly to standard normal. Okay, and let me again just to expand this a little bit. So that is, if I look at a fixed point on the real line, the distribution function of this thing will converge to the distribution function of standard normal, which is phi, as n goes to infinity. So there should be a limit here. N goes to infinity, distribution function converges. Okay, that's the statement. Let's prove it now. So the first step in the proof, it's going to consist of two steps. First, I'm going to assume that m is 0 and sigma is 1. Okay? In that case, what I'm looking at is Sn minus 0 over root n. I want to look at Sn over root n, and I want to find the characteristic function of this thing. And again, the strategy is to see that this converges. As before, this is the expectation of exponential it Sn over root n, which is the same as the expectation of it over root n times Sn, which you can write as the characteristic function of Sn taken at t over root n. And because the Sn is the n-fold convolution of the xi's, this is the individual characteristic functions of the xi's at t over root n raised to the nth power. Okay, so phi is the characteristic function of these IID random variables each. Okay, now here comes the lemma, the Taylor lemma, applied with n equals to 2. N equals to 2. So I have a k equals to 0 term, which just gives me 1. I have a k equals to 1 term, which gives me it and the first moment, and the k equals to 2 term, the square of it over 2 times the second moment, and an error term, which is smaller than that. So that's what I'm going to plug in now. And I have to not forget that we're looking at the characteristic function at t over root n. K equals to 0 is 1. K equals to 1 gives me an it over root n. Anywhere I had t before, I have now t over root n times the mean of the xi. Okay, k equals to 2 gives me 1/2 the square of it over the square of root n. So the square of it is a minus t squared, the square of root n is an over n, and then the second moment, okay, of the xi's, plus something that's smaller than this, little o in 1 over root n, but actually it's the little o of t squared over n as n goes to infinity, and all that raised to the nth power. Okay, now in our case m is 0, so this is 0. If we have a mean 0 random variable, then the second moment is the same as the variance. So this is the variance, which is sigma. So this is 1, and I'm just having here 1 minus 1/2 of t squared over n plus little o of t squared over n raised to the nth power. And now what happens is the same as before. As n goes to infinity, anything that's sublinear in 1 over n, so anything that's little of 1 over n doesn't make any contribution to the limit. The limit will only come from the 1/2 t square over n with the minus sign, and so that converges to e to the negative t square over 2, because that's what I have in front of the 1 over n. Alright, this is a characteristic function. It's continuous at 0, continuous at t equals to 0, and as we all know by now, this is the characteristic function of standard normal at t. Therefore, the continuity lemma concludes that Sn over root n converges weakly to standard normal. So that was step 1. Step 2, what happens if we have another mean or another variance? What if m is not 0 or sigma is not 1? Then life is actually easy. Everybody could repeat this proof, but it's actually easier than that. So in general, this is step 2. In general, if we have Sn minus Nm over root n sigma, which is the statement we want to look at, then what is this? This is the sum from 1 through n of the xk. And I'm going to take this opportunity to bring the expectations inside this sum and divide by sigma. So looking at the sum of this thing, whole stuff over square root n. These two are the same. The minus m summed up gives me the minus nm, the sum of the x is there, and the sigma factor is just going in and out of summation. And you don't see the denominator, so now you can. Okay, and what's the point? The point is that these random variables, these guys here, they are IID, mean 0, and variance 1. Everybody can check that easily. Okay, so therefore case 1 applies, and by case 1, this thing will go weakly as n goes to infinity to standard normal as needed.